Okay, so let us continue our discussion of contractions and minors. Uh, Let us recall what the things are that we have so far seen. We have already seen what contracting an edge in a graph means, and we have also seen what this thing means. G equal to mx, where g and x are two graphs. And we have seen this, we have proved this result that g is equal to mx if and only if x can be obtained from g through a series of edge contractions. So let us just also recall what this thing means. It means that for every vertex x in the graph capital X, there exists a subset Vx of the vertex set of G satisfying these four properties. The first one is this: for distinct vertices x and y in X, these sets, the corresponding sets are also distinct. Second, for each vertex x in X, the set Vx induces a connected subgraph of G. That means this induced subgraph of G induced by the set Vx is connected. The third thing is that these Vx's form a partition of the vertex set of G. This is a partition of this, and lastly and the most important thing is that for any two vertices, they are adjacent in X, that is xy is an edge in X if and only if there exists. So this symbol you probably already know, it denotes the phrase there exists a Vx Vy edge in G. So when all these conditions are true, then G is mx. Now we next further we move on with this. If this is a subgraph of a graph, some graph y, say, then X is called a minor of y, and we write, to express this fact in symbols, we write like this: X is a minor of y. And in particular, this means what? in particular any subgraph of a graph is a minor and still even more particularly every graph is a minor of itself. Okay, how are we getting this part? Let us see. So what we are saying here is this. It's like this. You have any graph y, you have found a subgraph of y, say g. Okay, so you move from y to g, and then it turns out that through some series of h contractions you get x, so that g is mx. When this happens, then we are saying that x is a minor of y. So that means you in fact can take, in place of g you can take y also. So that will give you the okay, not exactly that, but I said just now, that's not what I wanted to say here. What is written here is this: in particular any subgraph of a graph is a minor. So what, and that corresponds to this: you have any graph and you consider any subgraph g, and from g you go to x which is equal to g, and this is true in a trivial manner. G is equal to mg, and that is why any subgraph g of any graph y is itself a minor. If you are somewhat confused about this g being equal to mg, you can imagine it like this. You see, every x that is in this relation, any x that we may obtain through a series of h contractions, among those x's g itself is also a candidate, and you get g from g by performing no h contraction. Okay, it's just like among all the sets, the empty set is also a set. So among all finite series of h contractions, there is that one series where actually there is no contraction. If that also seems somewhat strange, you can in fact apply the definition of g equal to mg itself. For that, what we should have, you see, when do we say that g is mx? When all those conditions are true. In this particular case, that thing translates into this. Let me show here itself. You have g, and on this side you have g, which you are now viewing as x. So for every vertex in x, there should be one such set vx, which if you recall are called branch sets. So for any vertex in x, which actually is nothing but g, the corresponding branch set is actually that vertex itself, I mean the singleton sets consisting of these vertices. That definitely is a partition of the vertex set of G. So one condition is true. Also, for distinct points in X, the branch sets are distinct. That condition is also true. What about the subgraphs that these branch sets will induce in G? They are these single vertices themselves, which are of course connected, so that thing is also true. Moreover, if two such vertices in X are adjacent, then of course their counterparts, which actually are the same vertices here, they are also adjacent. So between these two branch sets, there is a, say this is X, this is Y, so this branch set is Vx, this one is Vy, so there is a Vx Vy edge, and that edge is of course this edge itself, and conversely also, obviously. So in a trivial manner, G is equal to Mg. So that is why any subgraph of any graph is one of its minors. That is, G is a minor of Y. And of course, every graph is a minor of itself, because every graph is a subgraph of itself. So that's what we are saying here. Okay, now we recall that result, which tells us that G is Mx if and only if X can be obtained from G through a series of edge contractions. So using that, what can we say about this minor relation? So that result is proposition 171. By proposition 171, let me write exactly what Diestel has written so that we can understand what he is trying to say. Any minor of a graph can be obtained from it by first deleting some vertices and edges. Any minor of a graph can be obtained from it by first deleting some vertices and edges. And then following that up with some edge contractions, that is, and then contracting her further edges. So in the general case where you have X there, this thing just says that because you can obtain X when G is Mx, you can obtain X from G through a series of edge contractions. So that's what the author is saying. Any minor X of a graph Y can be obtained from it by first deleting some vertices and edges. That corresponds to getting this subgraph G. You possibly have to delete some vertices and or edges, which actually also includes the case where you in fact do not delete anything. So you start with Y, you just have again Y, and then you do these edge contractions. So that takes you further from G to X. Conversely, if you use this operation, any graph obtained from another by repeated deletions and contractions repeated deletions and contractions is going to be a minor of the original graph, and these deletions and contractions can actually be done in any order whatsoever. Contractions in any order is its minor. And this fact of course is obvious when there is only one deletion. Say you are deleting one vertex or one edge, which actually gives you just a subgraph. So that is a minor, or any one contraction which of course gives you a minor, and which gives you an x, a possible x. This is clear for one deletion or contraction. And for multiple deletions and contractions in any order, the same thing is also true, and that comes from the fact that the minor relation is transitive and follows for several of these deletions and contractions. By the fact that the minor relation is transitive. From the transitivity of the minor relation, we will have to prove these things, okay? And in fact, not only transitivity, we are going to prove that the minor relation and the other one which we are going to see next, topological minor relation, they are partial order relations on the class of all finite graphs, and the result is proposition 173. Okay, so that's about our minor relation. Next we are going to go to the other version, the topological minor relation. So let's see what that has to offer. If we replace the author has written it in a somewhat very, anyway, let's just see what Diestel has written and then we will decipher it. If we replace all the edges, that means the edges of x with independent paths, and it needs to be properly I mean precisely said what independence means here, so that none of these paths has an inner vertex on another path. None of these paths has an inner vertex on another path or in X. Oh, so okay, we started with if, so the sentence ain't over yet. We call the graph G obtained a subdivision of X. And write, in that case, just like we had G equal to mx, in this case we are going to write G equal to Tx. And all these things will now become clear when we try to understand these things with an example, with the example that is given in the text. But let's just first complete writing this whole thing down. So again, just like mx, you recall previously for a given x, mx actually denoted not a single graph but rather a class of graphs. So here also for a given x, tx is going to denote a class of graphs. So that's what Diestel is saying. So again, Tx denotes an entire class of graphs. And that class is this, all those which when you view them as topological spaces, become homeomorphic to X. topological spaces in the usual manner, or what is the author writing in the obvious way. Are homeomorphic to X. The T, in fact, that's why we have the word T here. That other relation, there we had the word M, so which stands for minor, but in this case T stands for topological. The T in Tx stands for the adjective topological. If you are not familiar, you can in fact view any graph, any finite graph at least. I think it's in general true also for any graph, but for us the finiteness is enough. So you can view any graph itself as a topological space, where what you do, you replace all the vertices with some points, and you replace the edges with, you imagine the edges with homeomorphic copies of the unit interval, where the topology is of course the usual topology. And this thing, you can in fact make sense of this as your simplicial complexes, which are made out of simplices. Those things are there. Okay, we won't need those things. So at least the name topological minor comes from all these things. So if you let's just also go to this example, draw the graph, and then we will try to understand these things, and from there we will also see what this homeomorphism is about. Okay, so now we draw the graph example first. So in this example, as usual, there are many things. So first of all, let me just see. There is a square. And inside this edge, there are actually already two other vertices. So it's like this. This edge does not have any further vertex in it. This one has one, this one has another one. And there is a diagonal like one here also, and here there are three intermediate vertices. And that's not all. Outside there are many other things, and those many other things, I hope I do not make a mistake in going back and forth from here to there. First of all, here there are three vertices, and on this side we have three more. further, there are 1, 2, 3. Okay, so these 3 I have already taken into account, plus there are 2 more, and these outer vertices are all linked to one another in this way. What else is there? All these things are also there. This edge, then this edge. I hope the original one is retained. Okay, then this one, okay. And what about this? This is adjacent to these two, first of all, and now we are going to draw the inner links. The first thing is that these two edges, these two vertices on these two sides of the square or rectangle, whatever you may want to consider it, they are adjacent to this one lying on the diagonal. These two are adjacent to this lower one on the diagonal among these 3, and also these two are also adjacent to this outer one. Okay. And there is this. Is that all? Let me just so this is our y. Okay, so this is our y, and from y, just like before we had y, and from y we first considered one subgraph G, and then we considered mx, which turns out to be equal to G. That is, through a series of H contractions we got x from G, but G itself is a subgraph of y. So in this case this is y, and here again we are going to now consider one subgraph, and on that subgraph we are going to apply this although we cannot as of now we cannot view this as an operation done on G, because the way the definition, G equal to Tx, the way it has been defined, we started with x and not with G. So we are going to see what that means. So what we are saying, I don't have this part here now. So what we said is that if we replace the edges of x with independent paths between their ends, so that none of these paths has an inner vertex or on another path or in x. So first of all we have to say what x is, and that x, let me just use this part. To actually draw the other parts of this diagram. So from this y we are First of all going to go to tx, and then of course we go to x, and then that tx is g, and that tx is this. Whatever we have on and inside this rectangle. This is our G. So from this one we have got to this, and x is just this. Okay, so from y to g, then g to x, and g is tx. G is actually one candidate for tx. So let us now match this with the definition. So we have the graph x. So what we are saying, that we are going to replace each edge of x with independent paths joining their ends. That means, for example, you consider this edge of x, its ends are these two vertices. So we replace this edge with this path. Okay, the path having these four vertices, joining the ends, this and this, of the original edge. We do that with each edge. Here also we have replaced this edge with this edge of length, this path of length 2 by introducing an intermediate vertex. Here actually we have not done anything with this edge, but with this edge, just like this one, we have replaced it with a path of length 2, and these paths are independent in the sense that apart from, these ends, the ends of these paths may be, two such paths may have a common end. That's what I am trying to say. But the inner vertices are not common. That is, the inner vertices of one path do not lie on any other path, or in x. These inner vertices also are not parts of x, parts of the graph x. So let us just read again what Diestel has written. If we replace the edges of x with independent paths between their ends, independent in this sense, so that none of these paths has an inner vertex on any other path, all the inner vertices they form disjoint sets. On another path or in x, these inner vertices also are not nowhere there in x. Then we call the graph G obtained from x through this operation a subdivision of x. Okay, so G is a subdivision of x, and if some graph y contains a subdivision of X as one of its subgraphs, then we say that X is a topological minor of Y, which of course we haven't written here, but we will write. Now let us also see what this topological is about. It's just this. The paths become homeomorphic to this single edge in that topology. Actually, if you go down to the technical details, then there are some things, simplicial complexes, then for example, you are given a graph which you already know what it is, a collection of two sets where one set is a set of objects which are called vertices, and E is a set of two element subsets of V. So with this graph you can associate a topological space in a somewhat very natural way using the idea of simplicial complexes and connect such that many properties of the graph reflect on the properties of the topological space and conversely. For example, the graph is connected if and only if that topological space is connected, and such things are there. So if you go down to the details of those things, you will realize that this is isomorphic to this when you view these two things as topological spaces in that manner. Okay, so that's why this is called a topological minor. For some reason I am unable to speak today. Because of something I am a little distracted, that's the reason probably. Okay, anyway, so what next we are going to write, if G equal to Tx is a, just like before, subgraph of some graph Y, we call X a topological minor of Y. And in this text there is no special symbol for denoting the topological minor relation. Maybe there is a symbol, I don't know, but in this text no such symbol has been used. Okay, so that means this, of course, it looks quite complicated, but it just simply is some graph in which this subgraph has been considered, and you can go in the other direction and use the operation which is the inverse of what they are saying, that is replacing each edge with some path, so that the paths are independent in that sense. So if you go in the other direction, then you can get X. So and in that other direction, actually it's just simply this: you forget the intermediate vertices, the inner vertices, you suppress them, you just don't use them in drawing X. Whatever else you have, that in fact forms X. And the paths, so in this case, when you go from G to X, the paths are replaced with edges. That's the thing. So because you are removing intermediate vertices, you can notice one thing, that actually you are removing all the vertices which are of degree 2. So that's why this next paragraph has this: if G is equal to Tx, we view Vx as a subset of V of G. And call the vertices in Vx branch vertices. So these are the branch vertices. These vertices within the boxes are branch vertices. So it's like these vertices have not suffered anything. In this process of removing the inner vertices, they are intact, they stay just like they were previously in G. So that's why we view the vertex set of X as actually a subset of the vertex set of G. And the other vertices which have in fact vanished, they are called subdividing vertices because they subdivide. The other vertices of G are its subdividing vertices. This lower one we don't need anymore, but let's just for the time being keep those two things. Subdividing vertices of G, and we can of course also see that the subdividing vertices all have degree 2. Thus the subdividing vertices all have degree 2, whereas the degrees of the branch vertices do not change. Okay, they retain their degrees, while the branch vertices retain their degrees. Retain their degrees from X. Now before I move forward, I need ink. Next we come to the question of any possible relationship between these two relations, that is minor relation and topological minor relation. And there is a relation of course. So that is the next result. there is one more result in this section which says that both the minor relation and the topological minor relation are partial order relations on the class of finite graphs. That, however, we will not prove today. We are going to prove this one, which we are now going to state. So this is proposition 172. It has two parts. Every Tx is also an mx. Thus, every topological minor of a graph is also its ordinary minor. And this thing is almost trivial. Do you see why? That means what we are saying is this. You have you just look at this graph and this graph. This is a graph G, this is a graph X, and as we can see, G is Tx. But is it also Mx? Of course it is Mx, because the action of suppressing these vertices and getting one edge which replaces this entire path corresponds to a number of edge contractions, in fact. For example, you can contract this edge, say. So you get two inner vertices, then you contract that one, you get one inner vertex, then you contract that one also, and you get one path. So every such replacement of a path with an edge actually corresponds to a series of edge contractions. You do that for all the paths, so that ultimately you are getting x from G by nothing but some series of edge contractions. That's it. So that is why this Tx, that is nothing but G, is also Mx. And you can clearly see that this is true in general also. If you have a topological minor of some graph, then also that topological minor can be obtained from the original graph through a series of edge contractions in this manner. In the general case also there will be independent paths, so suppressing the inner vertices in them ultimately corresponds to a series of edge contractions. So every topological minor is also an ordinary minor, and there is in fact no need to write any proof for this. This second one, however, at first I thought it's very easy, but what can I say? It's not exactly obvious, although the author has not given any proof. If the maximum degree of our graph X is less than or equal to 3, then every Mx contains a Tx. Thus, this extra condition is needed. let us first complete writing the statement, and then we will try to understand its actual meaning. Things may be a little confusing, okay, at times, because sometimes we are starting with G and then getting X, and sometimes we are starting with X and then introducing extra things to X to get G. So we have to be extra careful. Thus, every minor with maximum degree at most 3 is also a topological minor. A topology, but what is Diestel writing exactly? Of a graph. Okay, we can write it in that way also. So he is mentioning that the minor is a minor of some graph. Is also its topological minor. So that means the author is saying this in this second part. We have some graph X where the degrees of all the vertices are less than or equal to 3, which is equivalent to saying that the maximum degree of the graph is at most 3. And you can then consider some G which is mx, which is an you see, this is the confusion I was talking about. This G is some graph of which X is an ordinary minor. Then there exists a subgraph of G of which X is a topological minor. That means there exists some subgraph. If you call this K, then X is K is Tx. So let's just match this with what Diestel has written. Thus, every minor, that means every minor X of what? Of some graph G with maximum degree less than or equal to 3 is also its topological minor. Topological minor means, you see, because we have mentioned that both the minor relation as well as the topological minor relation are partial ordered relations, so both of them are transitive. So if X turns out to be a topological minor of K, then automatically X is also a topological minor of G. Okay, so that's why we are saying it like this. Okay, let us now come to the proof. I'm going to say something here at this point, which I have said many times, but I'm still going to reiterate, is that all these videos, whatever the content is, may have some minor mistakes, inaccuracies, errors somewhere. So I leave that part entirely to you. Whenever you come across something that you either do not understand or you find it is just simply wrong, you please let me know. Some of you are actually doing that, and I am very grateful for that, because it's nearly impossible to go through all these things alone and not make a single mistake. Mistakes will always be there. Authors also make mistakes, and that's why they have errata, and in the subsequent editions of a given book they rectify those mistakes. So this is a process. It's not something like it's done and that's just it. That's not how things work. So let's just now see the proof. Part 1 is, we are just simply going to mention it's evident. Okay. Now what about part 2? In part 2 we have x, and every mx has to contain some tx. So let us see. So here what we are going to do, we are going to consider one particular mx, which is the least possible mx, that is the minimum mx with respect to subgraph relation. And we are going to start up like this. Since the minor relation is transitive on the class of all finite graphs, it's enough to assume that the mx that we are going to choose is minimal, or more specifically, the mx does not have a proper subgraph such that x is a minor of that proper subgraph. Since the minor relation, yes, it's enough to assume that g equal to mx does not have a proper subgraph say k, such that k is also equal to mx. Okay, so we have considered one g which is mx but which is minimal also, and this minimality will help us get our result. Now we are going to write all those things again. Because g is mx, we will have branch sets and those things. Since g is mx for every vertex x in x, there exists a, let's just mention the name, branch set Vx, which is a subset of V of g. It will be a repetition of what we started the video with, but it doesn't hurt to again and again write these things. If anything, they will solidify all the things in our mind. satisfying the following. For distinct x and y in Vx, the corresponding branch sets are distinct for each vertex in X. The subgraph it induces in G is connected. Three. The sets Vx form a partition of the vertex set of G, and 4 for any two vertices in X. They are adjacent in X, that is, they form an edge in X if and only if there exists a Vx Vy edge in G. Okay, so that's what it means for G to be Mx. Now the minimality of G will now tell us further about these branch sets Vx. Okay, let us see what next we get. Leaving these statements without proof, I don't understand what the author, what is he trying to do here? Maybe he is leaving these things without proof because these are preliminaries, no? So we can find these things elsewhere. But still, at least some hint would have been appreciated. This proof that I am writing here, this I found somewhere else. Since G is minimal, each branch set Vx is a tree. Let us see why. These things we have already seen twice by now, so there is no point keeping it. We know very well what these conditions are, so let me just wrap this part up. Okay, so there is X, which we need not draw again, but there is G, and in G we have the branch sets. So this is one branch set Vx corresponding to some vertex X in our capital X. Now what we are saying is that The subgraph it induces, of course, is a connected graph. So that is one of the conditions. But now what we are saying, this has to be a tree. What happens if it is not? If it is not a tree, then it has some cycle somewhere, no? And the vertices of this cycle are actually vertices in Vx. But then you just note that we are looking at G here. So this entirety is G. In G we have this branch set. Now if I have a cycle in this subgraph, actually technically speaking, strictly speaking, the branch set Vx is just a set of vertices, but simply I am showing so if you want to be absolutely strict with the things, so this is the subgraph induced by Vx. In this subgraph, say we have a cycle, but if we have a cycle, then without affecting the fact that from Gx we can get to x through a series of edge contractions, we can remove one of the edges of this cycle. Still, that same series of edge contractions minus this edge, of course, will take us to x. Do you see why? That is because what is x actually? Other branch sets are also there somewhere in G, and there are some interconnections, whatever, we don't know. So if you look at this thing from a distance and you treat these branch sets themselves as vertices and thinking of these edges that connect these branch sets as edges, then that is nothing but x, or a graph isomorphic to x. So whatever you are doing within one magnified view of a vertex of x is, it does not matter, it has no effect on the fact that after you collapse these branch sets and form x from G, you are again going to get that same thing. Whether this edge is there or not, it does not matter, because this edge is something that is happening entirely inside this induced subgraph, which has nothing to do with these interconnections of the branch sets. So that's why, and doing that, what do you get? You get a proper subgraph of G, from which also you get x through a series of edge contractions. That is, a proper subgraph of G which does not have this edge, that is G prime, is also mx, but that contradicts the minimality of G. We already said that G does not have such a proper subgraph from which you can get x through a series of edge contractions. That is why we cannot have cycles in these branch sets. So each branch set is a tree. Now there are further things, and those further things are this. Also, for each x belonging to the vertex set of x and each leaf let's just give it some name. Now each leaf, say ux, in the subgraph induced by Vx, which is now a tree, there exists a vertex. Okay, it may be a little confusing. Let me just first of all write it down carefully without any mistake, and then we will see what it means. There exists a vertex. So we have first of all chosen any x in X, and we have considered the corresponding branch set and hence the corresponding subgraph, which is a tree, and we have considered any leaf in that. For that, there exists a vertex y in this such that xy is an edge in X, and this ux is incident with the unique Vx Vy edge in G. This I can clean this part, because I am going to draw another diagram for this thing that we have written here. So let me keep some space for drawing that diagram. Unique Vx Vy edge in G. Okay, so here what are we then again saying? Also, let us start. For each x belonging to Vx, there is a branch set, and that branch set is a tree. Now we know it is any tree. We don't really know how it looks. Okay, that quite a few vertices, but anyway. So this is your subgraph, which is a tree induced by the branch set Vx, and we are again looking inside G. Now what we are saying, for every leaf in this tree, there are actually many leaves in this tree. One of them, say, is this, which we are, say, calling ux. There exists a y in the I think I have to draw x just to show what is going on. There exists a y such that x and y are adjacent in X, and such that the branch set of y that is Vy is such that this ux is adjacent to that unique Vx Vy edge that we have in G. The question is why unique? Because if you recall the example that we showed when explaining this thing, G equal to mx, that time also we had we drew one x and we had one G, in which actually the branch sets that we, so it looked something like this. The branch sets that we had between two branch sets, that linking edge Vx Vy edge was not necessarily unique. Actually, between this branch set and this one, you go back to that example, you will understand what I am talking about. There were actually multiple such connecting edges, but because of the minimality that we have in G, now multiple edges will actually lead us to contradiction, just like cycles inside this g vx led us to a contradiction. It contradicts the minimality of g. So because of that minimality, actually between any two branch sets where there should be such an edge, there will be a unique such edge. And now what we are saying is that for every leaf there will be another branch set such that the edge that joins these two branch sets should be an edge at this vertex, that is the vertex should be incident. All the leaves should be incident to these links between other branch sets, whatever link there should be. So for example, for this one also there will be another branch set where this should have a link. But why should we have a branch set for each such leaf? That is the question. No? Say you don't have this. Say the leaves are actually also leaves in the original graph G, that they are vertices of degree 1. Then again minimality is contradicted, because if you remove these leaves, if they are leaves in the original graph G, that process of going from G to X again is not affected, and in fact you then get, by removing this vertex, one proper subgraph of G, from where also you can get to X through a series of edge contractions. Do you see why? Because if there is no such link, then you can remove this leaf without any problem. But now if you remove the leaf, then the whole thing, it falls apart. You can then you cannot go to X. So that is why for each such leaf there should be a branch set, so that the connection is starting from here. For these other leaves also there will be branch sets. For all of them there will be one. Okay. But now, so we understand why this thing is happening and what we have written here. For each x belonging to Vx and each leaf Ux in GVx, there exists a vertex y such that x and y are adjacent in x, in capital X, and Ux is incident with that unique Vx Vy edge that G has. Okay. But now it is time for us to use this hypothesis. We are saying that each leaf needs a branch set, and that branch set of course comes from some vertex which should be adjacent to X, but there is a limit to the number of vertices that can be adjacent to X. There can be at most 3, because then X has degree 3 and it cannot be more than that. The graph X has maximum degree 3. So actually this branch set can be linked to at most 3 such other worlds, other globes, and that's where this whole thing, that is the heart of this proof. So now we invoke this condition and see what we get. Now, since, okay, so we have written this. Now since X has maximum degree at most 3, there exists a vertex Vx in this I should not use the notations in a wrong way. Vx has not been used before. Small vx, okay. There exists a vertex vx such that there exist, or let's just write there are paths in GVX from Vx to the leaves which are independent except for Vx. Okay, now again what is happening? So having at most 3 such other worlds, other universes, we understood. Now let us draw another diagram. So we are saying that because of this thing, this restriction, the tree that we see inside, it cannot be like this. Okay, let us first see what we cannot have. For example, GVX cannot look like this because this needs four branch sets besides this, to which this one is linked. You go down to x, that corresponds to x having one vertex of degree 4, which is not allowed. So what is going wrong here? I mean, whatever we have written, let us just first also see what we have actually written here. Because of this, there exists a vertex Vx here. Say you call this Vx, such that there are paths in this tree from Vx to the leaves. Of course there are paths because the tree is a connected graph. So from Vx to any other vertex you will have a path, and because it's a tree, that path will be unique. But something else is also being written here. These paths are independent except for Vx, which means that the paths don't have anything common in between them except that one vertex Vx, which is not the case here. You see, the path from Vx to this leaf is this, okay? From Vx to this leaf is this. These two are independent except for Vx. But when you look at the paths from Vx to these two leaves, one of them is this and the other is this. And they have, apart from Vx, this common vertex. And this problem is happening because here this condition is being violated. So I leave it to you to convince yourself that whenever there can be at most 3 leaves in Vx, because that's what we need here. No, if we don't have at most 3 leaves, then this is ultimately violated. Now you know why and exactly how. So there are, whatever the tree is, there are at most 3 leaves. So you consider the most complicated case, at most 3 leaves. in the most general case, you will in fact have one vertex which has degree 3 here, and not more than one such vertex. So because of that, you can take that vertex as Vx. Now the paths from Vx to the leaves are actually independent except for Vx, and these are linked to the other branch sets outside. That's how all the branch sets are going to look like. And this of course is only one case. The situation may in fact be easier than this. There may actually be 2 leaves. In that case, you can consider Vx to be any vertex here. And 2 leaves, of course, there cannot be 1 leaf. 2 leaves will at least be there. So either 2 leaves or 1 leaf. In any case, you are going to get a vertex Vx like this. Okay. So now the specific thing that will take you, the specific series of edge contractions that will take you from this G to your X, which is already always there in the background, is this, where you collapse this branch sets of course to X and retaining the interconnections, and that will take you from G to X, capital X. But at the same time, keep in mind that this is not just a minor relation which comes from applying those edge contractions, but it is also in particular a topological minor, because independent paths have been replaced with single edges. So that is why this next line is this. Have I written it here? So these edges are going to be, the topological minor relation that we are going to apply here. These edges, these particular Vx's, are going to be branch vertices of Vx, and the other vertices, whatever you have in the other branch sets also, they are going to be subdividing vertices, and you end up with this. Joining such paths together, these paths, we obtain a subdivision of X. Oh, so now, okay. So the author is writing from the other direction. We obtain, because I have got this proof somewhere else, so there it's written, but it's just a simple small paragraph. Behind all those things, actually, we have all these explanations. So that's why in this last part the writing is a little, it's going in the other direction. We obtain a subdivision of X that is a subgraph of G, because here I am just simply taking the thing down from what is written here. Subdivision of X, that is a subgraph of G with the set Vx as X varies over the vertex set of X as its vertex set. That is X is a topological minor of a subgraph of G. Let me write it here. Okay. Subgraph of G. And after this, of course, we have this proposition which says that minor relation and topological minor relation are partial order relations on the class of finite graphs. So that we are going to do in the next graph theory video. So here I end things, but before I really end things here, let me also mention that if this condition is not true, then it's not necessary that the conclusion is true. And to get a counter example, you take the Peterson graph. It has a minor which is not a topological minor. In the you try to generate that counter example. Okay, you work with the Peterson graph, you try to get, it's not very difficult, you do some edge contractions, you will see that you are getting a minor, but it is not a topological minor of that graph or of any subgraph of that graph. So that will be all for tonight, and tomorrow is again Saturday. Tomorrow means actually it's today, but still. So tomorrow, according to the schedule, what do we have? We are going to solve group theory problems from Gallian again. So that's just it. So I wrap things up with this. If you want to say some things about these things, positive or negative, whatever it is, you can write in the comment section below, or you can mail me at my usual address. The link will be there in the description. So see you tomorrow with group theory exercises from Gallian's Contemporary Abstract Algebra. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.